After my talk.
Yeah, exactly. I don't know how he did it. He arrived like 6:30. But I don't know. I couldn't do it because I would be like so dead.
Yeah.
I can't sleep.
Yeah. I was the same yesterday. I got back to my hotel at 3 and I just slept. Yeah. Hey. Yeah.
Okay, everyone. I'd like to introduce Josh. Josh holds a PhD in quantum information from the University of Western Australia and is now working for the quantum full-stack startup Xanadu in Toronto, where he's part of the quantum machine learning software team. And quantum open source project that he's actively working on includes Strawberry Fields and PennyLane. And today he's going to talk about quantum machine learning with PennyLane. So please welcome Josh.
Hi, everyone. So as Mark mentioned, my name's Josh. I'm a quantum software developer at Xanadu. And at Xanadu, we're a full-stack quantum computing company. So we're working on both the continuous variable hardware as well as open source quantum software development. So as mentioned, one of our software platforms is Strawberry Fields. This is for integration and submitting jobs to our quantum hardware. I encourage you to check it out, strawberryfields.ai. For the purposes of this talk, I'll be focusing on one of our other libraries, PennyLane, which is an open source quantum machine learning framework. So for this talk, I gave this a similar talk last year, introducing PennyLane. This year, I'll be going back a bit, discussing where the ideas for PennyLane came from, and also moving forward a year, so discussing what's changed in PennyLane over the last year since I last talked at FOSDEM. So starting off, PennyLane was conceived about July 2018. We were noticing that quantum machine learning had become quite a buzzword. The number of papers in quantum machine learning in the archive had started to increase significantly. And as we were in this noisy era of quantum computation, where we have these small-scale devices, people were wondering what could we do to combine machine learning with quantum computing, and what could we get out of it? So we sat down and we asked ourselves, why was deep learning so successful over the last decade or so? And it basically came down to 3 main points. Hardware advancements, so we'd seen GPUs have become immensely important in machine learning. The ability to scale up these thousands of small computations that people have been using in graphics for decades for machine learning caused a seismic shift in what we could do. And this is in addition to tensor processing units. So TPUs as well have sort of revolutionized what we can do in machine learning. In addition, the abundance of workhorse algorithms, so things like backpropagation, gradient descent, we were able to suddenly train massive neural networks using exact differentiation techniques that were much more stable than what we were doing previously. And finally, and this is probably a really large one, is specialized user-friendly software. So things like TensorFlow, PyTorch, JAX, these machine learning frameworks that most of you in the room are probably familiar with, these have done a huge amount to increase the accessibility of machine learning. Yeah, so this is kind of just leaning more into that. So you can see that the number of projects using TensorFlow have increased almost exponentially over the last 10 years or so. And as the industry has matured, these software frameworks are becoming more accessible, more easy to use, and there's more choice as well. So TensorFlow, PyTorch, JAX. The question is, can we train quantum circuits? So it was a question people had and people started playing around with in the quantum computing field. It turns out quantum computing is also differentiable. So you have a small quantum circuit which is controlled by quantum gates. these quantum gates take classical parameters. You perform a quantum computation on the hardware, and then you perform a quantum measurement at the end. And from these quantum measurements, you can compute measurement statistics. So you can measure certain quantum observables and take expectation values or variances. And these things are deterministic. If you put in the same parameters to this quantum circuit, you get the same output. So it turns out that these quantum circuits are differentiable. The outputs depend smoothly on gate parameters. Can we practically train quantum circuits, though? It turns out we can. And quantum machine learning methods called variational quantum algorithms have become one of the main near-term quantum algorithms for near-term devices. So this happened around 2011, 2012, 2013. Ideas started forming in the quantum community, things like the variational quantum eigensolver, which was a really neat idea at the time, saying that these variational quantum devices, they give us access to this enormous state space that we can't normally access with classical techniques. Can we train the classical parameters of these gates to generate a state that outputs a measurement statistic that we are looking for, that we want to find? So this is kind of, this variational quantum algorithm is described on the right-hand side here. So we have a quantum subroutine. This is a quantum black box. We just have quantum gates on our quantum hardware. We prepare a quantum state, and we have some circuit parameters that drive these quantum gates. We run the quantum circuit, we get a measurement output, and then we perform some classical processing and classical optimization. So we use techniques such as optimization and gradient-free optimization to update these parameters via some classical optimization loop. So this was first, these two algorithms mentioned up here, VQE and QAOA, these were sort of the first two major variational quantum algorithms, but since then, the field's really grown. And there have been natural extensions to other circuits and tasks that we've seen from standard machine learning. So things like quantum classifiers. Can we distinguish different quantum states by using this sort of variational quantum algorithm? Nowadays, there are many, many proposals just because of how well this scales to noisy devices. We don't have fault tolerance yet in quantum computing, but these algorithms seem to work so far very, very well on the noisy devices that we have. So what we want to do is we want to be able to train variational quantum algorithms, but we want to do them using some of the workhorse algorithms that have been developed over the last 10, 20, 30 years in machine learning. So one technique we have of doing this is called the parameter shift method. So initially, we were using gradient-free methods to train quantum circuits. This shifted a bit, and we started using something called the parameter shift method. So this is an analytic method of computing gradients coming out of quantum devices. So the main insight here is we're able to use the same quantum hardware to evaluate its own gradients. And this is a significant insight, because if we weren't able to do this, we'd have to classically simulate the circuit to get the gradient. And that's intractable. As the size of the quantum devices we have increases, you'd no longer be able to classically compute the gradient to perform this classical optimization loop. So you're constrained to gradient-free optimization techniques. So this is just a very short diagram that sort of demonstrates this parameter shift method. So on the left, we have our variational quantum circuit. It's an arbitrary circuit. We have a couple of gates running on the quantum device, and we have our input gate parameters and our output measurement statistics. All the parameter shift rule says is that if we take the exact same quantum circuit that we want to train, we shift the parameters forward by some value s, backward by some value s, and take the difference, the quantum device will actually output the gradient of the quantum expectation value at that parameter value. And the crucial thing here is that this shift is macroscopic. So it's not finite differences. We're not doing numerical differentiation. We're doing analytic differentiation. And we're able to get the output of the gradient with noisy devices, even when outside of regimes where we might be drowned by noise. So the quantum variational algorithms we've had so far have been quite simple in scope. They've been mostly maybe one or a couple of quantum devices, and we're getting the output of that quantum device, and we've got that classical optimization loop directly training this quantum circuit. So back in July 2018 or so, we were thinking, what if we want to do more than that? What if we want to do something like this? So we have an arbitrary computational graph. on this diagram here, the green boxes, the green nodes, those are quantum circuits. The yellow nodes are just arbitrary classical processing. And we want it to be as arbitrary as we want. Why can't we construct something like this? Say we have a machine learning model involving lots of classical layers. We want to replace a couple of them with quantum layers. We want to do something like that in open source quantum software, and we want to see what happens. So that's kind of where we were. We knew what we wanted to do. We wanted an open source framework that could interface with the accessible machine learning frameworks such as PyTorch, TensorFlow, JAX. We wanted it to drive real quantum hardware devices using these techniques for analytic gradient computation on real devices. And we wanted it to be accessible, intuitive, and allow you to perform arbitrary computations, mixing classical and quantum however you want. So we knew what we wanted to do. We weren't really sure what it should look like. So for this presentation, I actually scrolled up quite high into the deep, dark depths of my Slack history to see what we were discussing when it came to the UI of PennyLane. So I've got a couple of the messages here before I actually show you what the UI looks like. This is the very first one. The code should look as much like NumPy as possible. This was a very popular statement in our Slack channel when we were discussing the architecture of PennyLane. So there was lots of agreement there. We kind of got a bit distracted though. We started looking at context managers. We were like, maybe we want to train things using context managers in Python. We spent, I'm a bit surprised looking at our Slack history, but we spent about 2 to 3 days trying to make this work before realizing it's an absolutely atrocious idea. People don't want to train things using context managers. But hey, a quantum node is kind of like a function. You have input classical parameters. You have output classical data that's come from taking measurement statistics of your quantum device. You want to define it once, and then you want to evaluate it multiple times to be able to train it. So we started thinking, hey, quantum devices in this framework should just be functions that you call and compose with your classical functions. So that's kind of where we ended up. So that's our prototype on the left of what this quantum machine learning framework should look like. And that's what we ended up with. So in PennyLane, all quantum circuits are functions. Within these functions, you define your quantum operations. The functions take classical parameters, and they output measurement statistics. So this is just a quick overview of what a quantum machine learning task looks like in PennyLane. The main things we want to do with PennyLane, I've mentioned them slightly before, but just to reiterate, it's open sourced and developed openly. So not only is the code available on GitHub, but we also develop it openly on GitHub. So I think that's quite important, and that anyone who wants to contribute can look at our GitHub issues, look at our pull requests, and see the roadmap for where we want to take PennyLane. And this goes back all the way to the very beginning as well. If you go back through the history of the GitHub repo, you'll see all those ideas in terms of the UI and what we want PennyLane to do as pull requests and issues. So we want PennyLane to be functional. PennyLane is functional. It has a Python interface. It's designed to integrate seamlessly with the machine learning frameworks that we have right now, so NumPy, PyTorch, and TensorFlow. You can train a quantum computer the same way as you can with a neural network, and crucially, it's designed to scale as quantum computers grow in power. So in PennyLane, all quantum functions are executable on the quantum hardware we have available. So we have quantum hardware available over the cloud from Rigetti, from IBM. There are plugins available to connect PennyLane to that. And by just changing a couple of lines, you can switch what devices you're running your quantum functions on. So the main abstraction layer in PennyLane is, I've discussed this previously, but a quantum node. So the quantum node is what encapsulates your quantum computation. And that's the diagram there on the left. So you have your quantum circuit, input parameters, input state preparation, output expectation values, or variances, or samples, or probabilities. These are all things you can train on analytically in PennyLane. So the goal is that a computation is end-to-end differentiable. We want you to be able to use workhorse algorithms like gradient descent across your quantum classical hybrid model. So all quantum nodes in PennyLane will always be differentiable end-to-end, You can combine it with your other models in classical machine learning, and the entire computational graph will be end-to-end differentiable. So how do we do this? So with PennyLane, we support three main interfaces. We support NumPy, PyTorch, and TensorFlow. And the way this works is we accept the tensor objects from these three frameworks. So NumPy, if you're using Autograd and ArrayBox, the other two, a torch tensor or a TensorFlow tensor. When it comes time to evaluate the quantum portion of your computation, what we do is we just unwrap and extract the numerical value. We evaluate it. We use our formulas and internal architecture to evaluate the gradient, convert it back to a tensor object, and as well pass on the gradient information to the machine learning framework. So this is how we're able to make the entire thing end-to-end differentiable, even though we're using a mixture of quantum and classical hardware. So you can almost think of the quantum hardware as accelerators in a sense, similar to GPUs and TPUs. PennyLane is framework and hardware agnostic. So I mentioned previously that one of our hardware frameworks is Strawberry Fields. This is what we use to connect to our photonic hardware that we're developing in our photonic labs. In addition, we want to be able to mix and match. So as we're in the noisy era, there are advantages to our photonic technology. There are also disadvantages to our photonics technology. This is similar to superconducting qubits. This is similar to D-Wave's quantum annealer. All these noisy devices have their pros and cons. They have applications they're best suited for and applications that maybe are better in a different architecture. So we want to be able to combine these different frameworks, these different quantum devices. So you can take any of these. There are plugins available for Qiskit, Forest, Cirq, and Strawberry Fields, and combine them with either TensorFlow, pure NumPy for scikit-learn, or PyTorch. The cool thing is you can even, in one computation, have devices from different providers. So you can have for instance, this circuit down here on the bottom left, that's a photonic circuit. It's going into a classical processing node, doing the cosine and square root. And that's going up to a qubit circuit. So you can take a provider from Rigetti, take a device from Rigetti or IBM, combine this with a photonic device, train over the entire architecture. So for those familiar with machine learning, but maybe not quantum machine learning, here's a very quick example of what you can do. So we have a quantum circuit. We're rotating, we have one qubit in this quantum circuit. We're rotating the qubit around the x-axis, controlled by a classical parameter, doing the same thing around the y-axis, controlled by another classical parameter, and just measuring where this the state the qubit ends up in, measuring the poly Z expectation value. So this is pretty simple in PennyLane. You just create your device. So the device is just an abstraction for the QPU that you want to run and train your computation on. In this case, I'm using a QPU device from Rigetti Forest. You define your quantum function. So this is a Q node. It corresponds exactly to that quantum circuit in the previous slide. I've got my two rotations. I'm returning expectation value of the poly Z measurement. And the last part is just pure classical optimization, exactly like you'd see in a PyTorch or a TensorFlow machine learning example. In this case, I'm just using PyTorch to optimize. So I'm defining my cost function, which takes in the Q node, and I'm just optimizing that to reduce the expectation value of that Q node. So the key thing, I guess, is that the PennyLane Q node it makes PyTorch tensor quantum aware in this example. You can take a Q node and use it within PyTorch, and from PyTorch's point of view or TensorFlow's point of view, this function is a classical function that's end-to-end differentiable. So these examples are available on our website as tutorials. Just on the right-hand side is an animation of this short script actually running on a QPU. So we're training the qubit to enter the state that's defined by the cross on the block sphere, and you can see the qubit being trained and approaching the required state. So over the last year, we've worked hard on making PennyLane more accessible. So we want it to be a higher level abstraction. A lot of the other frameworks are They're object-oriented, they're low-level, and they're very hardware-focused. So you can access things that may be specific to a particular hardware, and things that we want to do sometimes. So sometimes we need to think about the underlying hardware that we're running our quantum programming on. At other times, we don't. We want to think in a higher level abstraction. We want to maybe do something assuming that the hardware will do the best it can based on the underlying framework. So that's kind of where we're positioning PennyLane. It's sort of the NumPy interface wrapping LAPACK underneath. So a couple of things we've added to the library over the last year to make it more accessible to provide an easier way of constructing your quantum machine learning models. Built-in library of circuit ansatz from the QML literature. So it's kind of an unanswered question about what quantum circuits ansatz are easiest to train and best for particular machine learning models and quantum algorithms. Papers are continuously coming out with new ansatz that provide benefits for different use cases. So these are easily accessible in PennyLane. We have a qml.templates library, and you can just include these in your quantum node. We heard feedback from a lot of users that said that they had code already using Qiskit or already using PyCore that they wanted to interface with their machine learning models, but they didn't want to have to rewriting it using PennyLane's interface. So we added the ability to import from these quantum libraries. So you can import your code from Qiskit, from QASM, from PyQuil, from Quill. It runs the same circuit, it gets converted into a QNode, and it just becomes end-to-end differentiable. So you can take your existing code and then interface it with PyTorch or TensorFlow straight away. So automatically adds analytic differentiation to existing PyQuil and Qiskit frameworks. Cool thing is you can take these programs loaded from Rigetti Forest, convert it into a QNode, and then deploy it on other quantum hardware if you'd like. We're also working on adding optimization that's maybe better suited for a quantum landscape. So things like the quantum natural gradient. So taking into account what the cost landscape of your variational circuit looks like in order to ensure better convergence. So this is internal research that we've been working on at Xanadu. This is just an outline of what this algorithm looks like. It's a kind of a quantum equivalent to the natural gradient, if you've heard of that, which takes into account classical Euclidean space when you're doing gradient descent. Quantum natural gradient takes into account the quantum geometry when doing gradient descent, and in general can lead to much better convergence with variational algorithms. So this is just a plot comparing for a couple of circuits, gradient descent in blue versus atom in green, and then quantum natural gradient descent in red and black for different approximations. We've also heard feedback that people want their simulations to be faster. So with PennyLane, we took the approach that it was hardware first. If you defined a QNode, it should always be executable on hardware. But there are shortcuts we can take with classical simulators. One of those is if we write the simulator using TensorFlow or PyTorch, for example, we can do classical backpropagation techniques that scale better in certain regimes. So PennyLane now includes a tensor network simulator. Built using Google's tensor network software and TensorFlow. So this uses classical backpropagation inside the QNode to compute the gradient, which if you have a lot of parameters can be faster. So enables routines where maybe you're training your quantum circuit on a simulator, you get your trained parameters, and then you deploy using test data on the quantum device. We also have a new quantum chemistry plugin. So right at the beginning of the talk, I mentioned that one of the first variational quantum algorithms to really create this QML 2.0 wave was the VQE algorithm, the variational quantum eigensolver. So this algorithm allows us to use quantum computers to probe the electronic molecular energies of various molecules. So PennyLane now interfaces with another open source quantum library, OpenFermion, by the quantum team at Google. So using OpenFermion, you can convert any electronic molecular structure to a set of quantum observables, and these are now importable into PennyLane for training on quantum hardware. So the other thing we really want to do is I mentioned at the beginning we want to make it accessible, and part of that is the UI and what frameworks we interface with. Another part of it is having good documentation, stable API, and collection of tutorials for people to explore how to use PennyLane. So if you go to pennylane.ai/QML, please check it out. We have a constantly growing collection of quantum machine learning tutorials using PennyLane across a mixture of different hardware devices, hardware frameworks, and also machine learning frameworks. And these are things from just looking at variational quantum eigensolver, looking at quantum state preparation, to things such as quantum transfer learning, doubly stochastic gradient descent in quantum systems, quantum structure learning, etc. So please have a look. This not only is PennyLane completely open source and developed in the open, but the pennylane.ai/QML website is open source and on GitHub. So any of these tutorials that are available there can be downloaded, can be edited with pull requests, and we also accept pull requests for new tutorials. We also have a Twitter account, PennyLane AI, so please follow, and we try every week or every 2 weeks to tweet out new QML results we see, as well as new tutorials that are available using PennyLane. So we wanted to see where we could go with PennyLane once we had this base UI, this base abstraction. We noticed that the core abstraction in PennyLane is this QNode concept. So a quantum device corresponds to a quantum function in Python that is an end-to-end differentiable and can be used with any framework. But we started to notice that it wasn't enough for us as internal researchers at Xanadu. We needed the ability to process these QNodes at a higher level abstraction. We found that we would have groups of QNodes, and we wanted to work with these groups of QNodes without thinking about the low-level quantum circuit within each QNode. And this is something that happened when we were thinking about VQE. Essentially, the VQE module was two things. It was a mapping operation. We were taking a quantum circuit and mapping it across different return values, different expectation values we wanted to measure, and then a reduction operation. Once we evaluated all these different quantum nodes, we wanted to just take the dot product between these quantum nodes and coefficients that defined the problem we were solving. So we wanted a better abstraction for working with groups of QNodes that was algorithm independent. We also noticed that we were getting to the point where multiple QPUs were available right now on the cloud. So if you're using IBM, there are, I think, 5 or 6 IBM devices available for the public. So if you sign up to their accounts, you have access to multiple devices right now. The same thing is available on Rigetti Forest. There are, I think, 2 chips now available on the QCS, Aspen 4 and Aspen 7. So maybe a year ago, we were getting excited by having access to 1 device, and that was fine. Now we have access to a couple of devices, and it can be frustrating at sometimes. Now that we know we can have more than 1, we want 1,000. So we started thinking, what can we do with, rather than have a single big QPU, which is what a lot of hardware providers are working really hard to get towards, what could we do in the interim if we had 1,000 small QPUs? So we recently introduced the concept of a QNode collection. So a QNode collection is a group of QNodes that are evaluated, that can be evaluated independently. So they can be evaluated at one go, asynchronously. At the same time, we want it to be an abstraction that you don't have to think about too much. And a common way for creating QNode collections in various quantum algorithms is you map a ansatz or template over measurements. So we wanted to extend that as well. Not only can you map a ansatz or a quantum template over measurements, but you can also map it over devices. So I have a small example of what this looks like here. So here I have a quantum circuit ansatz. It just does 2 x-axis rotations. Both of these parameterized, and then it does a C0, which is a quantum entangling gate. Then I have a list of observables I want to measure. So these are just 2-qubit tensor observables. I want to measure poly X cross poly Z, and I also want to measure poly Z cross poly X. And then say I have access to 2 devices. So in this example here, I'm just using the Rigetti Forest QVM simulator with two devices that are currently available on the simulator, Aspen 4 and Aspen 7. So previously, you would create two Q nodes. You would be forced to evaluate them sequentially, as you normally are in Python. We introduced a way to do this that makes it slightly simpler. So you can use this new QML.map operation to map your ansats over both your observable list and your list of devices. Say what you want your measurement to be, and the output of that is not just a single Q node, but a collection or a group of Q nodes. And these group of Q nodes are treated as one single object in PennyLane. So in this example here, you have some parameters, you pass it to your Q nodes, both of the quantum devices are evaluated at the same time, and you get your results back as a single NumPy array. And the really cool thing about this is because we have access to these devices that we can access at the same time, it's embarrassingly parallelizable. So we've added this asynchronous dispatch support to PennyLane. So this is experimental. It's only recently been added. But if you call your Q nodes normally, in this case, it takes about 5 seconds. If I pass the parallel equals true argument, PennyLane's dispatching both of these quantum circuits to be evaluated at the same time. You get your results back in almost half the time. So we added this ability to create Q node collections, but we also want them to be easy to use. So we introduced some high-level high-level processing functions that allow you to compose your Q node collections with other classical processing functions from your machine learning libraries. So things like qml.sum, qml.dot, qml.apply. So in this very simple 3-line example here, I'm creating so I'm using PyTorch in this case, creating a tensor of observables, tensor of coefficients rather. And then you can see in the second line, I've got my Q nodes, and I'm just composing it with a whole bunch of different classical processing functions to manipulate the output of these Q nodes. And with the ability to manipulate Q node collections in this way, we've gone from something that might take 10 or 15 lines in Python to something that only becomes a single one-liner in Python. So in this particular case, I'm applying the torch sign function to my Q nodes, and I'm performing the dot product between the sign of those Q nodes and the coefficients I just defined. All this happens lazily in PennyLane, so the quantum evaluation only ever happens when you actually evaluate your Q node collection, your cost function. So the third line here, when I'm calling my new cost function with the parameters, that's when the dispatching happens, and PennyLane starts dispatching the quantum computations to the external quantum devices and performs the classical processing. So I hope this talk has kind of given you guys an idea of our vision for quantum machine learning at Xanadu. We want quantum machine learning to be intuitive, accessible, be easily explored, and we want anyone to have the ability to run quantum machine learning algorithms, whether it's on simulators or actually on hardware that's available in the cloud. We want quantum machine learning models to be widely shared and re-implemented by others. So that's sort of the impetus behind the PennyLane.ai/QML collection. Circuits should be reusable, embeddings, pre and post processing should be easy. We want that to be something that you don't have to think about. We want the documentation to be able to be designed so that you can find these things easily, and that maybe you don't even have to look at the documentation. Rather than searching throughout what methods are available, you just find a function in PennyLane that applies that thing for you, and you can do function compositioning on your quantum devices. PennyLane is open source, development is open source, and I think as Thomas mentioned in his first talk, a lot of the physicists working on quantum open software at the moment, a lot of the developers are physicists. I'm a physicist, a lot of my team are physicists, and sometimes it helps to get feedback and contributions from people outside of physics. So something we'd love is for people in this room to have a look at our open source code, have a look at the issues that are opened, and see if there's anything they feel they can contribute. Because maybe from someone outside of physics, you guys can add features or implement things in a way that we would never have thought of doing ourselves. So thank you. Got some links at the top. So this is our Twitter link and our QML tutorials page.